Okay, I'm going to be doing a few problems from the practice quiz that I assigned on Thursday. So let's just get started. Number 2, object A has 4 times the mass of object B, but only 1.5 times the total momentum. What is its velocity relative to object B? So this is kind of a proportions type of a question where I give you factors, like something has like 5 times the kinetic energy, what's its velocity relative? It's like one of those types of questions. And so I'm going to try to show you, this is I think the second time or third time I've shown this, an easy way to solve these problems without having to come up with sample values and like practice, you can solve it that way and you'll always get the right answer, but there's an easier way to do it. So I'm just going to start just mentioning that that momentum is just simply this. So in terms of the mass of A times the velocity of A equals the momentum of A. Just in general, that's what momentum is. Okay. Now, the way that you want to do a problem like this, where you're dealing with factors, is that you don't know what the actual mass of these objects is. All you know is that they're factors. Object A is 4 times the mass of object B. It's got 1.5 times the total momentum. So if you think about these factors, I'm going to do this in pink. This mass has a factor of 4 sort of attached to it. The momentum has a factor of 1.5 attached to it. And we're trying to figure out what is the overall factor on the velocity. So the way you want to do these is to substitute in your factors for these variables. What I mean by that is we're going to rewrite this now as 4VA equals 1.5. Again, the reason we're doing that is because if both A and B have this unknown m, then you could say this is m, and then you could say that the momentum of A has some m, and then B has like a 4m, whatever. But it's just easier to deal with it the way I'm showing you. So do a substitution, take out the m, and just put the factors in. Take out the p, and it's a factor of 1.5. We're trying to figure out what the factor of the velocity is. Well, that's going to be easy. It's going to be 1.5 divided by 4. So 1.5 divided by 4, 0.37. So what is this velocity relative to object B? It's 0.375 times the velocity of B. That's the factor. It's 0.375. There we go. So again, that's the best way to do those, is to just substitute the variables with the factors that you're given. All right, 3. Caleb jumps off a cliff, lands in the water. So just imagine this is a falling object question where he's going to hit the water with some final velocity here. And now that final velocity, there's going to be a force, and it's going to take him to some depth, D or H, whatever you want to call it, what variable you want to call it. You could even call it Y if you wanted to, just because it's in the Y direction. But this is really the essence of the question, what's happening right here. So, excuse me. We are given the initial height that he falls, 55 meters, and we've got a mass, and we've got a time interval in the water. And that's when his final velocity in the water is 0. Well, the problem really starts when he hits the water, right? Right when he hits the water. So we got to figure out what is his velocity when he hits the water. It could be a force and motion question. Probably just easier to use conservation of energy. So real quickly, he has initial PE. It's going to be converted to KE. So mgh is equal to 1/2 mv squared. And I'm not going to show you all this because I've done this a trillion times. V is now square root of 2gh. Okay. So how fast does he hit the water? Well, it's 2 times 9.8 times 55. Take the square root. Looks like 32.83. 32.83 meters per second. Okay. I'm just putting a square around it because we're going to need this value. It's not like a final value. So what is the force of water on Ben? Okay, now we can really start this problem. He has some initial momentum. He's going to lose that momentum due to the impulse provided by the water until he stops. And so there's no momentum left over. So that's what the equation is going to start with. Your initial momentum when you hit the water This is going to be the impulse provided by the friction with the water until you stop. And there's no momentum because your velocity is 0. So what is the force of water on Ben? Okay. The easiest way to solve this is we're going to solve for F. So I'm rewriting this. You can bring the Ft over to this side, divide both sides by t, and you end up with the momentum divided by t equals F. The initial momentum. Remember, this is the momentum when he hits the water. So this is going to be m times v when you hit the water. I'm going to call that vi because initially when you hit the water. That's going to be t, which was given. And now we can solve this thing. Its mass is 36. The velocity is 32.83. The time interval is 2.13. I'm not going to solve this, but that's how you would do it. Okay, this is how you could get the force of the water. If there's a sharktopus 32 meters below the water surface, will he be eaten? Okay, so this question is now really getting to this variable d. How far does it go? Before we begin, I want to point out, I'll use green, that there is nothing in this equation that's going to have a d in it, right? Because momentum is mv. There's no possible way to use strictly momentum to get d. You could, let me just rewrite it here. You could, sorry, let me just rewrite it as it was written. So we initially had this. You could get the t from the problem. You could figure out what the acceleration is from the force, and then you could use VF squared to get the d. I mean, you could go that route if you wanted to, using force and then motion. Oh, in this case, actually using momentum and then force and then motion. But again, there's an easier way, and that easier way is energy. You hit the water with some initial kinetic energy. You lose that energy due to the work done by the water, the friction with the water, until you stop. So notice the similarities between how you treat this with momentum up here and how it looks with energy. It's very similar. So you have 1/2 mv squared minus the force of the water on you until that work done by water takes away all your kinetic energy. The good news is we are given mv. We already solved for f, and now we can just quickly do d. So I'm just going to algebraically solve for d. That is going to be, you'll have mv squared all over 2. That's just the 1/2 mv squared. I'm just making the 1/2 look like over 2. Equals fd. So we want to solve for d. So mv squared all over 2f equals d. And that is how you're going to solve this thing. You're given m. You solved for v. Your v was at 32.83. And you already have your f. That was from up here. And that's how you'll get your d. Last question, 8. You have a bullet traveling until it hits a piece of wood on a surface, and it's asking for the wood's velocity after the impact, and it embeds. So this is an inelastic collision question. So I didn't really give you a ton of space, so I'm just going to make this solution down here. I lied. I am actually going to do it up here because this part A is going to take a little longer. So this is going to be the mass of the bullet times the velocity of the bullet plus the mass of the wood times the initial velocity of the wood. And since they stick together, it's going to be an inelastic collision where the two masses combine and they travel together at some velocity at the end. All of the momentum comes from the bullet because the wood was at rest. So the mass of the bullet is 0.03 kilograms times 300 plus 0. That's the momentum of the wood. And that has to equal the combined mass, which is going to be 5.03. It's this plus this is this. I'm just running out of space. So now if we want to solve for VF, it's going to be 300 times 0.03, and we're going to divide that by 5.03, and we get 1.79. Okay. So that's how we'll do the first part. So now the wood block with the bullet in it slides, and because of friction, it's going to stop. It's going to stop right here at a distance d, which they give you, and we're looking for the mu sub k. So notice that they give you a d. So this is most likely going to be a work and energy type question for this part, where now we're going to be able to solve using the conservation of energy. You have some initial kinetic energy. You're going to lose that due to the work done by friction until you stop. And that's where the 0 comes from. Which means 1/2 mv squared minus the force of friction. The force of friction on a flat surface is mu sub k times mg. Right, here's the normal force is m. Remember, friction is mu times the normal force, and on a flat surface, the normal force is mg. So I should probably write that down. So force of friction is mu sub k times the normal force, and the normal force is mg. So that's where this stuff comes from. We can factor an m out of everything. So that'll go away, that'll go away. And we're trying to figure out the mu. So let's just algebraically solve for mu. So the way this looks to begin with is going to be this equals mu sub k gd. I just brought this whole thing over to this side. And now we're going to divide both sides by the gd. So v squared all over 2gd equals mu sub k. And since you have all those values now, you can just solve for mu. And that's how we would do this one.